My name is Alexander Mark, and I am a graduate student at the University of Illinois at Chicago, funded through CDAC. I am working under Professors Russell Hemley and Juan Carlos Campuzano on experiments involving the ultra-high compression of cuprate superconductors. These experiments have been supported by the faculty and students from UIC listed here. We have had assistance at APS Sector 16, HPCAT, for taking all structural measurements. Additional sample prep was performed at APS Sector 13, JSE CARS, and samples were provided by Paul Chude's group at the Texas Center for Superconductivity. Cuprates have always had high critical temperatures, starting from the tens of Kelvin and going up. The first superconductor discovered with a critical temperature above the boiling point of liquid nitrogen was a yttrium-based cuprate. The bismuth family of cuprates, bismuth, strontium, calcium, copper oxide, abbreviated as BSCCO, is one of the most commonly studied members of the cuprate family due to its relative stability and already high critical temperature. The three common members of the BSCCO family are abbreviated by the number of heavy metal elements, such as 2201, 2212, and 2223. The last number is indicative of the number of superconducting copper oxide layers in a unit cell. Upon compression, Tc tracks the oxygen doping, which is a parameter that is known to dramatically alter the charge carrier concentration within the superconducting planes and therefore Tc. Above a critical pressure, however, all varieties of BSCCO break away from this pressure-induced charge transfer model, and Tc climbs monotonically. The major goal of this study is to see how high we can drive Tc via an external pressure. Samples of pure phase BSCCO 2212, 2-layer, and BSCCO 2223, 3-layer, were loaded in diamond anvil cells, and the chambers were cryogenically filled with neon gas at APS Sector 13. Ruby and gold were used as pressure standard. Samples were brought up to 100 gigapascals, about a megabar, with X-ray diffraction patterns taken every 2 to 3 gigapascals at HPCAT, which is APS Sector 16. Both mixed phase and pure phase patterns were refined to generate compression data. Previous compression experiments by Olsen et al. Up to around 60 gigapascals, a planar collapse was observed in the 2-layer BSCCO variant. This collapse occurs in the same pressure regime as the second rise in Tc as seen in transport data. Additionally, anomalous growth in the A parameter was seen in compression experiments by Zhang et al. It should be noted that all other experiments were performed using a methanol-ethanol mixture as a pressure transmitting medium. We now believe these anomalies are non-hydrostatic effects due to the methanol-ethanol mixture freezing and giving a preferential compression direction. Our samples were in a neon environment, which is known to be much more hydrostatic. Data was fit to a Vinet equation of state, but a single equation did not adequately explain the entire curve. There appears to be an isostructural phase transition where the bulk modulus dramatically increases, corresponding to a stiffening of the C parameter. This is reflected in the Ni seen in the unit cell volumes around 20 gigapascals. The fact that the dramatic increase in Tc occurs irrespective of the pressure transmitting medium implies that whatever mechanism is responsible for superconductivity in the cuprates effectively ignores any collapse due to non-hydrostatic stress. While there appears to be no planar collapse in the C parameter of BSCCO 2212, there is a saturation in the C over A ratio above approximately 20 gigapascals. This is due to a dramatic decrease in the compressibility of the C parameter. The A parameter appears to decrease with no deviations from a Vinet equation of state. In the 3-layer BSCCO samples, a saturation in the C over A parameter was not seen to the limit of the experiment, and a single Vinet equation of state was used to fit the data. We believe that, when placed in a more hydrostatic compression medium, there is no planar collapse in BSCCO 2212. Tc does, however, appear to grow above a critical pressure in all pressure transmitting media, irrespective of hydrostaticity. The planar collapse observed in BSCCO 2212 by Olsen et al. Appears to be unrelated to the second rise in Tc versus pressure, and is a non-hydrostatic effect. Any anomalous growths in parameters observed by Zhang et al. Were also non-hydrostatic effects. At approximately 15 gigapascals, the C over A ratio of BSCCO 2212 appears to saturate. BSCCO 2223 does not exhibit this flattening out in the equation of state up to the maximum pressure attained, and certainly not within the range of the increase in Tc. We are currently preparing transport experiments to see how high we can raise Tc in both BSCCO 2212 and 2223. Thank you, and here are the works cited in this presentation.